Ladies and gentlemen, welcome to the first talk of our morning session. Our speaker is Xie Chen from Caltech University. She's expert in quantum circuits. She's going to talk about quantum circuits as a lens into quantum phase and phase transition. Please join me to welcome our first speaker.
Well, all right, great. Good morning, everyone. I'm very happy to be here and talk about my work. This is my first time at ICBS, so very pleasant place. So I try to make this talk very general. So if you don't know me, I'm a condensed matter theorist at Caltech, which means I'm a physicist. I'm not a mathematician. My talk will be full of physics jargons. And I understand that not everybody speaks the same language, so if you find anything confusing, please don't hesitate to stop me and ask questions. We have a small audience, so that's nice. I have all the time, I have 55 minutes. That's a lot of time to address questions. So hopefully we can be very interactive. So as I said, I'm a condensed matter theorist, which means I'm interested in the topic of phase and phase transitions, and especially in quantum phase and phase transitions. And you can see probably from the title that we're trying to take a slightly different approach than what conventional condensed matter textbook will teach you about. Usually a condensed matter textbook starts by talking about crystals and electrons and band structures and so on and so forth. We try to take a different way of thinking about things. On the one hand, it's because that the kind of quantum phases and phase transitions that we're interested in are sort of unconventional, meaning that they're beyond what usually people think about in terms of condensed matter system like magnetism or superconductivity. We try to talk more about topological order, something more exotic. And because of that, we need to deal with strong interaction and strong many-body entanglement in quantum systems. That's kind of crucial to our story. And because of that, we need some new tools. So the conventional tools of band structure and maybe perturbation on top of that is not quite sufficient. So we want to bring in actually quantum information ideas like quantum circuit and use that as a way to probe into the structure of the phase diagram of quantum many-body systems. Okay, that's just about the title, just a brief introduction of what I'm going to talk about. Okay, so let me just jump into it and try to just present the story starting from the beginning. And this is phase and phase transition, of course, has been the topic in condensed matter for decades, if not hundreds of years. And there are phase diagrams that people understand well. For example, this is the phase diagram of water. We know there's liquid, solid, and gas, and there are transitions, blah, blah, blah. And now the new frontier is, of course, about quantum systems. And even about quantum systems, we already know a lot. For example, we know there can be insulator, semiconductor, superconductor, and so on and so forth. But we are particularly focusing on quantum system, especially at zero temperature, and then with strong interaction. And here we consider generic strong interaction, not one specific type, but we're kind of like open-minded and say, what if we allow any kind of local strong interaction? So particles interact locally, but otherwise we don't really restrict on the type of strong interaction the particles can have. Okay, so you can imagine a phase diagram that looks roughly like this, where we have all kinds of conventional or unconventional phases, ferromagnet, superconductor, but also quantum Hall, and topological order. And on top of that, we can talk about transitions. There can be first order transition, second order transition, or even exotic things like the deconfined quantum critical point. So usually how progress is made in condensed matter, and you probably hear a lot about them in the news or you go to APS March meeting, is that there's new materials discovered, right? The hottest candidate in the field currently are these two-dimensional materials like graphene, and people take multiple sheets and they put them on top of each other and even twist by a little angle. So that's called Moiré twisted graphene, or maybe not graphene, some other materials. And then people put a lot of probes on it, and their experimental data. On the other hand, theorists make a lot of predictions about what can happen and try to both predict and also explain experimental result. And there's a constant interaction between the two sides. And that's how new discoveries are made and new progress comes about, usually in condensed matter. And I talk about that because we take a slightly different approach. I'm more a theorist than the previous approach in the sense that we don't start from experimental observation. In particular, we try to consider the generic setting of strongly interacting many-body systems, not really restricting to the kind of strong interaction that's realizable in a particular material. And then we just prescribe certain generic features of the system, like what is the dimension of the system, what is the symmetry, and then we allow any potential local interaction to happen. And then we ask a really, really big question, which is what phases can exist in principle? This is not usually how people do things. Usually we say, oh, this is a material, what is happening there? But we ask from the other perspective and ask what can happen in principle, and how to potentially classify all possibilities, all possible phases. And what are phase transitions like in principle, and whether that actually happens in a material is a next question. But at first level, we ask what are the possibilities? And it turns out, and these are of course very ambitious questions to address, and of course the fact we can potentially answer these questions is because there has already been so much discoveries starting from real materials and all the experimental data collected. But as we try to take this more top-down approach and try to answer these, in a sense, more systematic questions, we learned that quantum circuit can play a very important role. Okay, so you can see that instead of starting from real materials, we kind of take a more mathematical approach. I feel like I'm justified to speak here. We try to give a definition of what is a phase. That's not usually how physicists do things. But we try to say, okay, can we define things? And once we define things, can we try to come up with toy models that's solvable, that can show all kinds of properties? And then hopefully to connect with real materials, we'll perform numerical simulation. And then eventually, hopefully, there will be real materials. But in a lot of situations, we don't go that far, but that's okay. And even if we don't go all the way to real materials and experiments, this approach has been fruitful in the sense that it's more systematic, and sometimes it gives us surprises. That's something we don't expect to see in real experiment. We can find them starting from definition and toy models. All right. Right. So let's talk a little bit about definitions. It's usually, if you open the math textbook, it starts from definition and theorems and proof of theorems. If you start from a physics textbook, it usually doesn't define something at the beginning. But quantum phases is a concept that's so prevalent that people actually do have some level of definition. So this is a classic textbook by Sabir, where he talked about how to think about phases, basically saying that if there's if you go through a phase transition, then you're out of a phase. So transitions, singularities and non-analyticity at the transition defines a phase. So for us, as I mentioned, we find that definition is good, but sometimes it can be helpful to reformulate it in a different way. And actually, we're going to reformulate it using quantum circuits. So back in 2010, we had this paper where we considered so-called gap phases, meaning that quantum antibody system where okay, where where the ground state is separated from all the excited states by an energy gap that's strictly bigger than zero, okay? Even as the system size goes to infinity. So this is the kind of system that we call gapped, and because we're considering zero temperature quantum phases, then we only need to focus on the ground state space. Okay, so for gap phases, the phases are defined, of course, according to Subir, that if everything's smooth, if no singularity exists along a path, then two systems will be considered to be in the same phase, right? So this is from a Hamiltonian perspective. If we have a Hamiltonian description of a system and we change the Hamiltonian and nothing dramatic happens, everything is smooth, everything's gradually changing, then they're in the same phase. So like a magnet or superconductor. But we find it useful to interpret this definition by thinking about what happens to the ground state, because we're thinking about zero temperature and there's a gap, so this isolates out the wave function, the state at the lowest energy. So if we consider what happens to the ground state as we smoothly deform the Hamiltonian from one form to the other without closing gap, without any singularity, then what happens is that quantum physics says that there's an adiabatic evolution for finite time that connect the ground state on the one side to the ground state on the other side. This is just textbook statement. And then we take one more little step and interpret this finite time adiabatic evolution as finite depth circuit. So you can see that there's not much we're doing, but we kind of changing perspective from talking about phases in terms of Hamiltonian to talking about phases in terms of states. Okay, and just to be sure what I mean by quantum circuit, it's just the same quantum circuit that people talk about in quantum computation, where you can have qubits, local degrees of freedom to act on, and then there are quantum gates, these unitary transformations that act on the quantum qubits. Of course, in quantum computation, the goal is to perform some quantum algorithm to factor numbers, to simulate quantum system, etc. But here, we're going to use it to define phases and see how to, actually later I'm going to talk about how to connect between different phases. Okay, so these are some of the popular quantum gates that people talk about. There can be single qubit, 2 qubit. So you hear a lot of news about the fidelity of these gates. That's what people like to brag about. And starting from these bunch of qubits, we can apply a bunch of quantum gates. And one very important feature of these quantum gates is, again, their locality, because in condensed matter, locality is a very important input. So here, for example, we can have 2 local quantum gates, and then we can apply a bunch of them, non-overlapping, so they're all computing in the same layer. And then we can apply another layer, potentially overlapping with the one in the first layer, but then non-overlapping within the second layer. And then we can go more and more and more. And the number of layers is another thing you might hear a lot in the news that these quantum computing companies like to brag about. It's called the circuit depth. Okay? In the quantum computing experiment, circuit depth basically means the time they can run their quantum computers. Okay? Because the circuit has to be applied one layer at a time. So The higher the depth, the more you can do, the more capability you have in your computer. For us, it's very important that we restrict ourselves to something called a finite depth quantum circuit. Of course, finite compared to the system size, because in condensed matter, we're always imagining that the system size is infinity. There's a dimension, but once we set the dimension, we take the limit of system size going to infinity as a chain, as a plane, or as a cube. But then the circuit depth, the number of layers of circuit that we can apply will be restricted to be finite, because that's what we derive from this smooth deformation of Hamiltonian. If we use finite depth quantum circuit to connect wave functions, we're guaranteed to stay within the same phase. But if we use something that's bigger than finite depth circuit, then we might get out of the phase. Okay. So the finite depth quantum circuit kind of serves as an equivalence relation between ground state wave functions in the same gap phase. So this is basically what we were talking about back in 2010. And the nice thing about finite depth quantum circuit is that it keeps everything local still local. So if we had an operator starting from this red qubit, and then after the finite depth circuit, it's going to grow a little bit, but it's going to grow by a finite amount. It might grow to a 3-qubit operator or 5-qubit operator, but it's going to be a finite number. Okay, so this is just trying to convince you, without showing you any rigorous math, that this finite depth quantum circuit can actually be used as an equivalence relation to relate wave functions in the same gap phase. So it serves as some kind of definition of gap phases for us. And from there, we define concepts like short-range entanglement versus long-range entanglement. Basically, short-range entanglement is something that can be generated by a finite depth circuit, and long-range entanglement is something that cannot be generated by a finite depth circuit. And you might say, oh, this is a lot of words, and you can define things, fine, but what can you do with it? It turns out that this picture of having short-range entanglement and long-range entanglement is actually very useful, because back in the days, back in 2010, when we were writing the paper, there was another very big topic, a very hot topic going on, which is called topological insulator. You must have heard about it. Charlie Kane and Fu Kane and people, they were talking about 2-dimensional, 3-dimensional topological insulators and superconductors, lots of experiments. So that's the ideal situation for condensed matter. And very soon, there were even a classification table by these people in this paper, a full classification of all possibilities of topological insulators and superconductors. So it seems like, oh, the problem is solved, and it's just the experimentalists need to do their work and find the material. But actually, it's solved in a limited context, because this is the classification within the free fermion setup. Okay, so if you have fermions and they don't interact, or at least if the interaction doesn't do anything dramatic, then this is the classification table. But if we do have fermions that have strong interaction, actually that's quite a lot of situations like that, or if you have bosons and they have strong interaction, it's not clear. Oh, thank you. This is spatial dimension. This is 1 spatial dimension, 2 spatial dimension, all the way to A. So you can see kind of a periodic structure in the classification. That's really nice. So the question we were faced back in 2010, around the time, was the classification. Well, if not classification, but rather just how to think about phenomena like topological insulator, but in a strongly interacting setting. And if we start from the free fermion picture, we're not going very far. We need to start a band structure. We talk about band structure, but it's very hard to get to the strongly interacting limit. But it turns out this short-range entanglement and long-range entanglement picture actually provide the crucial insight. So what we realize is that the phenomena like topological insulator is actually something part of this bigger idea called symmetry-protected topological phases. That is, it needs symmetry protection, like time reversal or charge conjugation. Charge conservation. But if symmetry is preserved, then there's something non-trivial, and especially there's some edge states going on around the insulating bulk. So taking that to the strongly interacting limit, we came up with this construction or classification, in a way, of symmetry-protected topological phases in strongly interacting systems by realizing that the entanglement pattern in these states are short-ranged. Okay, so if you have a one-dimensional symmetry-protected topological state, through finite depth circuit, you can disentangle them into short-range entangled pairs. And in 2D, if we apply some finite depth circuit, we can disentangle everything into short-range entangled plaquettes. So we were able to construct toy models using these short-range entangled patterns, and then systematically realize the so-called symmetry-protected topological order in any dimension with any symmetry, well, mostly unitary symmetry. And it does not fully classify things in 3-dimensional and higher, but it captures most of things. And it's a very systematic way of constructing things. Good. So that's what we did back more than 10 years ago. So this is 2012, more than 10 years ago. What we were basically saying is that if you have a finite depth circuit, you can move around within the same gap phase. And that gives you, you can even construct interesting short-range entangled states using this idea. But a very obvious question that we wanted to address but didn't know how to address was how to jump between gap phases. Okay, so if you have multiple gap phases and you want to jump between them, what should we do? Well, according to the conventional perspective from the Hamiltonian approach, then people would say, oh, you deform the Hamiltonian, the gap closes, there's some singularity, some correlation function goes to infinity, and some specific heat goes to infinity, and then or goes through a jump, and then there's a phase transition. Okay, and of course, the question for us is whether there's a useful quantum circuit description of that process. Okay, because from there we'll see what happens to the entanglement structure of the wave function. So this red arrow, whether there's a circuit description of this red arrow. We know there's gap closing, but it's not clear what kind of circuit would do that. And of course, the reason we want to answer this question is because it can potentially give us insight into phase transitions, which is something even more interesting than a gap phase. A gap phase does not have much response, but phase transition have all these universal response functions. Try to follow the line of thought we had, but I'll show you why it took us more than 10 years to answer this question, because if we naively follow this line of thought and say, okay, there's an adiabatic evolution, and you change the Hamiltonian, and the gap closes, and we can follow the adiabatic evolution, right? Of course, the problem here is that the adiabatic evolution, the gap closes, so the adiabatic evolution will take a very long time. You need to be very slow near the critical point. And it takes time that's at least linear, because usually the gap closes as 1 over L. L is like the linear system size. So the time it takes is at least linear time. Okay. So it seems to indicate that we need a linear depth quantum circuit. It seems that linear depth quantum circuit would be the answer. On the other hand, it's very suggestive that this might very well be the answer, because somebody proved in 2006 that if you want to map between gap states in different phases, linear depth is the lower bound. Okay, so they prove things for like trivial state to the symmetry breaking GHZ state, or trivial state to topological state, and they proved that linear depth is at least the lower bound, meaning that we need a very high circuit depth to map between the two sides. Right, sorry. Right, maybe I can draw it here. That so usually, let's say we have consider 2D system, and the size is L by L, and the linear means L. Linear means proportional to L, some constant. Right, the depth of the circuit would scale linearly, would be proportional to L. Right, so it seems like we have the answer, but we also know that this answer is not good enough because this is sufficient but not necessary in a way, or the other way around. Because we know that the generic linear depth circuit is going to be too powerful. Okay, so if we start from disentangled qubits, just everything product state, we can apply some local gates to entangle them, and we can apply another set of local gates to entangle locally among all of them. But if we apply a circuit depth that's linear, it's going to generate entanglement all across the system, right? In some way, the entanglement length is going to be comparable to the system size. So everything is going to be entangled. And in fact, it's going to lead to something called entanglement volume law. If you cut out a subsystem, entanglement is going to be too big. And that can generate states at very high energy, and even lead to something called information scrambling and chaos. And that's another exciting topic. But for us, we want to stay at 0 temperature and talk about gap phases. This seems to be too much. Okay, so if you remember, for finite depth circuit, it's a necessary and sufficient equivalence relation. We're guaranteed to be able to reach every corner of the phase, but we're not getting out of the phase. For linear depth circuit, it's going to take us out of the phase, but it's probably going to take us to some crazy place. Okay. So we know that this answer is not good enough. And that's why we get stuck for 10 years. And then in 2024, while doing some other topic, we realized, oh, actually what we need is just to put an adjective in front of linear depth circuit so that we consider only a subclass of it, and then that's going to be our answer. Okay, so we have this diagram, this very pictorial way of we thinking about the quantum states, where this is the corner of gap states, and within each gap phase, we connect them with finite depth circuit. And of course, if we apply a generic linear depth circuit, we're going to get somewhere critical, thermal, highly excited. But if we apply just the right amount of quantum circuit, we can map between gap phases without going into very high energy. And it turns out that this kind of circuit is called sequential quantum circuit. So starting from finite depth circuit, we're taking another step. We're saying that this sequential linear depth circuit is the next level of quantum circuit in terms of clarifying the structure of quantum phases. Okay, so let me show you what this means and where it's going to take us. Okay. So let's consider the simplest example of quantum phases and phase transitions. This is the model that all condensed matter classes are going to teach. It's the so-called Ising model on one-dimensional spin chain. You have a bunch of qubits. So here by X, I mean the poly X on qubit. And the Z is a poly Z operator on qubit. And it's well known that with a Z2 symmetry, this two Hamiltonian represent two different phases. And this one was just sum over magnetic field in the X direction, will polarize all the spins in the X direction and lead to a symmetric phase. While the other one, while the other one, oh, I know, if I press this one too long, it's going to shut off. If I, this Ising coupling is going to lead to so-called spontaneous pressure breaking. where all the states want to be in either 0 or 1 state, and then there can be a superposition between them. So if we impose the global symmetry of all the x multiplied together, this is a Z2 symmetry, then these two are two different phases. This is symmetric, this is symmetry breaking. And there has to be a phase transition in between. This is like the canonical example of quantum phase transitions at 0 temperature. Okay. And then we can, of course, for us, the question is how do we map between this purely product state to the all 0 plus all 1, so-called GHZ cat state. About cat state, people are also referring to this kind of big superposition state. It turns out that people already have written circuits for generating these states because people were considering like in an ion trap or a neutral atom. And once they have the quantum computer, they want to generate entangled states like this and how to do that. And this is the circuit. So the circuit has a bunch of steps. So you have some pi over 4 rotation on the first qubit, and then a pi over 4 rotation of this ZZ coupling on 1 and 2, and then repeat that pattern on bit 2 and 3, and 3 and 4, and 4 and 5, so on and so forth. So if the details actually doesn't matter, but what matters is that if you look at the structure of the circuit, it's composed of 2-qubit unitary transformations on the first 2 qubits, and then 2-qubit transformation on the second 2 qubits, and so on and so forth. So eventually, if we want to cover the whole system, this is like a staircase structure, and you can only do one step at a time because these gates don't commute, so you cannot do them at the same time. You need to do them one step at a time, and to cover the whole system, of course, we'll need linear depths, right? We need a linear layers to complete the circuit. But on the other hand, this is a very special kind of a linear depth circuit because in each layer, there's only one gate. Okay. And in a sense, this is like sweeping from the left end to the right end and following the sequence of moving to the right one step at a time. So this is what we now call, a sequential linear depth circuit. And you can verify that this circuit actually indeed does the job because it maps the Hamiltonian from one side to the other and back. And then there's a linear depth, but it follows the sequence of going from left to right. Okay, so this is the, yes. Right, exactly. So great question. Because this is all unitary, so the gap actually doesn't close. So what happens is that you start from a Hamiltonian, let's say, of this form, and you kind of flip the terms one by one and grow a bubble of the second phase inside the first phase. And the bubble keeps growing, and there's a domain wall between the two, and eventually the bubble covers the whole system. So it actually doesn't directly go through the phase transition. Right. So the second example is more non-trivial. This is the everybody's favorite topological example where we can have, we start from a product state and we want to map to this famous toric code state. I won't talk about the details, but the idea is again that we have a sequential linear depth circuit that can do that. The circuit goes like this. First, you apply a bunch of gates to the first row, and all these gates, they commute with each other, so they can be applied at the same time. So this is a depth one-dimensional circuit, one time. And then we move on to the second row and apply the same circuit to the second row. But the second row doesn't commute with the first row, so they need to be applied one at a time. Okay, and then the third row and the fourth row, and eventually in the last row, we need to turn our head 90 degrees and then apply the gate one by one and fill in the blanks and eventually close up the whole system. So this circuit, you can see that it has a circuit depth of Lx plus Ly. So this is again linear depth, and it follows the sequence of row by row and eventually column by column. Excuse me? Oh, here I'm considering a torus, 2D torus boundary condition, but you can also talk about other boundary conditions. And this linear depth doesn't applies to all boundary conditions. Right, so these are, of course, just examples of, in general, what we call a sequential circuit. You can consider one-dimensional chain where the sequence is like from left-hand side to the right-hand side. For a two-dimensional system where it's patch by patch or row by row or even radially, there can be all different sorts of patterns. And we try to define it in a way that's, and the reason that it's actually useful for thinking about mapping between gap ground states is that, so we try to define it in a way, that's independent of the patterns. And the way we define it is by saying that we want a quantum circuit where each local degrees of freedom is only acted upon by a finite number of gates. For example, here, if you stare at this qubit, it's only acted upon by 2 gates, right? And here as well, 2 gates. So the nice thing about having a finite number of gates acting locally is if then we take an entanglement cut, like here and here, the entanglement increase, the entanglement change is only coming from these local gates. So it changes only by a finite amount. So it preserves so-called entanglement area law. And if we start from something with a gap, and the folklore is that nobody proves it except in 1D, that if you have a gap, then there will be an entanglement area law in the ground state. And since the sequential circuit preserves the entanglement area law, we would like to argue that we also preserve the gap of the system. Of course, none of that is proven, except in 1D. Yes, this picture is trying to show how it preserves entanglement area. Yeah, so in 1 dimension, area law means that if you take a segment, the entanglement is finite. Okay, and because the circuit changes it by this 2-qubit unitary here and 2-qubit unitary there, the change is only finite amount. So if we start from something with a finite entanglement for a segment, then after the circuit, it's still a finite entanglement per segment. So this is area law for a 1-dimensional system. If you have higher dimensional system, you have a 2D system like that, and we make a cut like this, and we'll see that there's only a finite density of gates along the cut. So per unit length, you only see a finite number of gates, so the change to entanglement is only, again, finite per unit length. So that's, again, it keeps entanglement area law, which means that entanglement is proportional to the length of the cut. Right. But other than that, we see that a sequential circuit can be totally powerful. So apart from, while it preserves entanglement area law, it doesn't preserve a lot of other things. For example, it doesn't preserve locality, which was the case for finite depth circuit. It doesn't preserve short-range correlation. It doesn't preserve short-range entanglement. And that is exactly the feature we want because we want to be able to map between different gap phases with different correlation and different entanglement patterns. So we can start from the trivial state with no correlation and no long-range entanglement. And then we can map to symmetry breaking GHZ state with long-range correlation, symmetry protected topological states with some non-trivial edge state potentially. And then we can also map to fractional topological state with so-called long-range entanglement, and even exotic fracton state, which was the topic I was studying before this, but then it somehow led us to the sequential quantum circuit. So as physicists, we don't prove things. We didn't prove that a sequential circuit is all powerful in mapping between all gap phases, and actually nobody knows what are all the gap phases. But what we did in the paper were that we were pretty exhaustive and tried to map between all the gap phases that we know up to 3 dimension and show that a sequential circuit can be constructed to map between. Okay, so this is back to this picture, and we show that apart from this finite depth circuit that maps us between states within the same gap phase, we can use the so-called sequential linear depth circuit to map between states of different gap phases. And this is the more satisfying answer than just saying linear depth circuit, because it's not going to take us out of the region because it preserves the entanglement area. Okay, I still have 15 minutes, good. So you might say, okay, where do you want to go from here? I explained to you that the finite depth circuit as a very abstract concept was actually useful for us when we were trying to answer the question of how to generalize topological insulators and superconductors to the interacting setting. Okay, so here by thinking about how to map between gap phases, of course, the original motivation was to look into phase transitions, and as you pointed out very nicely, that this sequential circuit doesn't really take you through the transition point, because when we deform the Hamiltonian, we're kind of taking the whole system and change it uniformly, change it everywhere, and so that it has to go through this critical point to go to the other phase. But sequential circuit is kind of doing something else. It's growing a bubble of the second phase inside the first phase, so it kind of avoids the criticality along the way. So everywhere is gapped, it's entanglement area law. So the question is, can we still see some phase transition feature using sequential circuit? And this is actually a paper, hopefully we'll be able to put out this month. Well, there's not many days left this month, so maybe next month, where we claim that sequential circuit actually is what people talk about in field theory in terms of so-called generalized symmetries. And generalized symmetries play a big role in the study of phase transitions. So that's why we hope that sequential circuit will give us more insight into phase transitions. So this is very much ongoing work, but I'll try to give you an idea of what we hope will happen, at least. All right. So first of all, this idea of generalized symmetry, I was just starting to learning about it in the last couple years. Obviously, it existed in various other fields for quite some time already, and it's a very interdisciplinary topic. So I like this diagram, which was, I think, these people at the KITP program, they came up with it. So it's an intersection between high energy physics, quantum gravity, math, condensed matter, and by talking about it in terms of quantum circuit, we hope to introduce also the quantum information perspective into this. But that'll be too many sheets. So 4 is perfect. 5 is too many. Anyway, so you see that there's a lot of collaboration on that, and it's if you're from a high energy perspective, it's been around for a while. And for me, one of the most, this is how I understand generalized symmetry. So usually when we talk about symmetry, for example, from the simple Ising perspective, we have some predetermined idea of what a symmetry looks like. If we have an Ising chain, symmetry looks like a spin flip on every spin, right? So if you have a bunch of qubits, and if there are quantum bits, and then the spin flip will be implemented by this X operator everywhere. So it's a tensor product of X operator everywhere, a tensor product of local unitaries. This is usually what we call symmetry, or maybe anti-unitaries. That's as far as we go. So you can do spin rotation and maybe anti-unitary of time reversal, but not much beyond that. Of course, once we start to learn about these so-called symmetry protected topological phases, we have to face something called anomaly. And as a realization of anomaly on the lattice, where I'm most comfortable with, what we realize is that we can't have symmetry like that. A tensor product of local unitary operators these kind of symmetries never have anomalies. If you want anomalies, you want to go beyond these kind of operators. And it turns out that in a very simple setting, for example, if we're considering the boundary of a two-dimensional Z2 symmetry protected topological phase, then the effective anomalous symmetry on the boundary looks like this. So you have the spin flip everywhere. And then you also have this 2-qubit phase gate between every pair. So between particle 1 and 2, there's a phase gate. Particles 2 and 3, there's a phase gate. And then so it's phase gate everywhere. Okay. So this is very weird because the first row doesn't commute with the second row, but we know that what is this? This is a depth-2 quantum circuit. Okay, so this so a finite depth quantum circuit, which doesn't necessarily have the tensor product structure anymore, can realize anomalous symmetries. This is what we learned from the SPT work. Okay, we go from tensor product of unitaries to finite depth circuit, and then we can go even further. Okay, and then the most popular example people talk about in terms of these generalized symmetries, and especially I would recommend this review paper by Shu Heng, which very nicely talk about the so-called non-invertible symmetry between the two Ising phases, the symmetric phase and the symmetry breaking phase. Okay. So it's well known that there's a duality transformation, this Kramers-Wagner duality that maps in the symmetry breaking phase. That's been known for decades. And it turns out that this sequential circuit that we came up with is exactly realizing that duality. We didn't start wanting to do that, but of course, the result is the same. Because effectively, as I mentioned, through this circuit, we're mapping the Hamiltonian term x to ZZ and ZZ to x. So mapping symmetric phase to symmetry breaking phase and symmetry breaking phase back. And this is exactly what the Kramer-Wagner duality is expected to do. Okay? And you can say, so if we are at this critical point where the coefficient in front of these two terms are equal, then this is a point where the symmetry is satisfied. Okay, so this is a symmetric point with the Kramer-Wagner symmetry. But this Kramer-Wagner symmetry, you can see, is very different from the usual kind of symmetry we talk about, right? Because it doesn't even have an inverse. So one of the axiom of symmetry in quantum system is saying that it's either unitary or anti-unitary. But now people are going beyond that because the Kramer-Wagner duality, you multiply it with its dagger, it's going to give you 1 plus the total symmetry. Okay? It only acts on the no charge sector. It doesn't act on the charge sector. Oh yeah, it's one-dimensional. So if it's periodic boundary condition, it's still fine. If it's open boundary condition, then the boundary might be messy. If periodic boundary condition, it should be fine. Yeah. Yes. But our usual setting is infinite chain, and then we specify, okay, maybe periodic boundary condition. Right. So this is what people mean when they say, oh, this is a so-called non-invertible symmetry because you multiply the operator with its dagger, and then it doesn't go back to identity. Okay. And then we see that from a quantum information perspective, why this is an unusual symmetry is because it's actually realized by the sequential circuit. It's not realized by tensor product of unitaries. It's not realized by finite depth circuit. In the previous two cases, they both have inverse, right? Because in the previous two cases, we can both find inverse to these operators, but here this becomes non-invertible. Oh, yeah. Right. So anomalous means that it cannot have a tensor product structure, but if it's non-anomalous, you might imagine just doing some 2-qubit basis transformation to make it not on site, but then there should be a basis transformation to take it back. I think there's some recent work by Wilbur on that. Yeah. So if you just generically give me entangled many-body operator, there should be some way to detect whether there's an anomaly. Okay, good. So that's pretty much where we are at this point. We're seeing this connection between sequential quantum circuit and generalized symmetry. And as I advertised, we're going to post this paper of sequential circuit as generalized symmetry on lattice. So starting from the definition of generalized symmetry, we can derive that it has to be implemented as sequential circuit once we put it on the lattice. And that connects to a lot of things like gauging, the idea of duality and topological defects, and all these things are very important at critical point. So I can't say more concretely more about critical point, but hopefully these will give us more insight about what to think about interpretation. So this is very vague, but that's where we hope we'll go. Okay, so finally, let me thank all my collaborators, brilliant collaborators, and yeah, these are publications, and the one that's upcoming, I don't think it's here yet, but that's with Nat and another graduate student of me, Xing. So thank you.
Quantum phase transition usually look at the finite temperature. So I look at the scaling function controlled by this quantum critical point. So, so I will have to go to finite temperature. So how this sequential circuit model bring you things into this finite temperature, mixed state, or scaling?
Yeah, so far we have been only thinking about phase transition at 0 temperature. We're not going
At the end of the
into
day, you have to go to finite temperature.
maybe we just think about 0 temperature transitions. I mean, 0 temperature phase transitions still exist, and they're a topic, and you can potentially do something about them. And then of course
But
you can
physics,
say
the physical measurable quantity are all at finite temperature.
or you can say like quantum Hall. They do exist, right, at 0 temperature. So experimentally, people measure them, and you measure the transition as well. So if the temperature is low enough, hopefully we do access the 0 temperature features. Yeah. So of course you can say whether there are new features, and very importantly, people nowadays talk a lot about these mixed state phases and transitions. And very interestingly, a large part of this mixed state effort is trying to reformulate the finite depth criteria in terms of finite depth channel. So because in mixed state, there's not a, or at least people don't try to formulate things in terms of Lindbladian having a singularity. They try to formulate it as density matrix being connected as finite depth circuit. So hopefully this whole thing also translates into something about finite temperature.
More questions? Can I ask you?
Yes.
So when you say that you can classify somehow gaped phases, do you see the difference in the case when your quantum circuit is built from the integrable Hamiltonian or non-integrable?
Oh, no. We don't distinguish between that, right? The integrable ones, I don't really know if there's any difference between using integrable Hamiltonian and non-integrable to do the circuit, right? But that's an interesting question. No, I don't have anything concrete to say.
Okay, thank you. Thank you again, our speaker, for her talk.